Students, am I audible? I think due to like network disconnect, I just have been disconnected. Is it now audible? Is it clear for everybody? Everybody is able to hear me? Just tell me in the chat box quickly. Okay, fine. Okay, I'll just repeat it once. Okay. Okay, fine. So now coming here, what I just was speaking about is about binary heap. Okay, binary heap means it is complete binary tree. Complete binary tree is what we call it as binary heap, but the array implementation. Okay, array implementation of binary, complete binary tree is what we call it as binary heap. Okay, so then what is complete binary tree? Complete binary tree is when you take a binary tree. Binary tree means every node maximum 2 child. Every level of the tree should be completely filled. Last level, the filling should happen from left to right. And while filling from left to right, all the nodes should be available. No node should be missing. For example, when you take this example, see all the levels are filled. Coming to last level, it might be like incomplete, but the filling should happen from the left side. So this can be called as complete binary tree. This can be called as complete binary tree, but this cannot be called as complete binary tree because without a left side node, a right side node is coming. So filling should come from left to right, and every node you need to fill, and then you should go to the next node. So, okay, so every level, if you see completely filled with the last level, the filling should happen from left to right. That's what complete binary tree is all about. Then when you just come to binary heap, there are two different types of binary heap is there. One is min binary heap, the other one is max binary heap. So coming to minimum binary heap, if you look at the complete binary tree, any parent, if you take the parent value should be less than or equal to child value. And when you take any like tree, what is maximum binary heap? When you take any tree, the parent element should be always greater than or equal to the child element or value. So this is the difference between minimum binary heap and maximum binary heap. Where in minimum binary heap, any parent, if you take the parent element have to be less than or equal to child, and any like the maximum binary heap, any parent, if you take the parent should be greater than or equal to child. Okay. So then, let me scroll down and maximum binary heap. So one example of maximum binary heap, we took certain example 21, 10, 35, 12, 42, 29, 15. Okay, let us just take this particular example. Okay. So now coming here, first we took 21 and we created a node and we inserted. Next I took 10, and this 10, either the 10 can be inserted to the left of 21 or to the right of 21. I inserted to the left of 21 because that is what complete binary tree filling should happen from left to right. So I need to maintain that complete binary tree property. So I'm just inserting it to the left. And after inserting it to the left, I'm comparing the child. I'm considering the inserted element to be the child. And I'm taking the parent element of it and comparing 10 and 21. Which, I always want, according to maximum binary heap, always parent should be greater and child should be lesser. I think that's true here. Parent is 21, child is 10. So a parent is definitely greater than the child. So 21 and then 10. Then what is our next element? 35. That 35, I will insert it to the right of 21. So 35, and that has been inserted to the right of 21. And after inserting to the right of 21, now I need to consider that as a child. Okay, now I need to consider that as a child, and I have to take parent and I need to compare. So child and parent, which is 35 and 21, if I compare, child is being greater and parent is being lesser. So I need to make a swap between both of them. So whereas 21 and 35, we will have a swap. So 35 will become like parent node, and 21 will become child node. Okay, 35 parent node and 21 is going to be child node. So now this is actually following the property of complete binary tree, as well as it is following the property of maximum binary heap as well. What is the next element? The next element is 12. Okay, next element is 12. So when you just simply take this element 12, okay, so 12 is going to be, we're going to insert this 12 to the left of 10. And after inserting this 12 to the left of 10, okay, 12 to the left of 10, I need to make a swap between 12 and 10, because when 12 is a child and 10 is a parent, if I consider, according to max binary heap, parent should be greater, child should be lesser, but it is not following the property. Child is greater, parent is lesser. So I need to make a swap between both of them, where 10 and 12 will be swapped. So 10 and 12. So which means 12 will go up, 10 will be the child. Then I just come to 42. So 42 is going to be the right child. So 42 is going to be the element. Okay, right child, 42. So after inserting 42, let that be child, and the parent is actually 12. So when I compare this parent 12 and child 42, child is greater and parent is 12. So I need to make a swap between both of them. So 42 and then 12. Okay, 42 is here, parent is 42, and child is, like 12 it becomes. But I should not stop with one swapping, one checking, because that 42 might also, like conflict with its own parent now. So what I need to do is, as I just checking the child and parent, now again I need to place, I take it as a child and find its own parent 35 and make a comparison between both of them. Child is greater, parent is lesser, which is not the property of maximum binary heap. So again, I will make one more swapping. So 42 will become the root node now, and 35 will come here. Again, I will take this 42 as a child node, but there is no parent node for that, because that becomes the root node of the entire tree, right? So once if I reach the root node of the entire tree, I can stop. Or otherwise, if any parent child, like conflict is not happening, that place also we can stop. Okay, that place also we can stop. Then what is the next element that I need to insert? 29, where 29 will be inserted to the left of 21. Okay, 29 will be inserted to the left of 21. 21 is inserted to the left of 21. Okay, 29 is inserted to the left of 21. Now I need to like compare, like this, taking this 29 as a child and 21 as a parent, we need to make a comparison where 21 child between both of them. So 21 and 29 will be swapped. So 29 is a parent and 21 is a child. After this, let me take this 29 as a child and let me make the root node as a parent. And if I make a comparison between both of them, I think parent is greater, child is lesser. Okay, parent is greater, child is lesser. There is no conflict over here. So I will stop my checking process here. What is the last value? Last value is 15. I will insert it to the right of 29. So 15 will be inserted here. And now when I compare this 15 with the 29, parent is greater, child is lesser. So no conflict. So I don't need to do anything. I stop my checking process. Now when you look at this entire tree structure, this is also a complete binary tree. At the same time, that maximum binary heap property is also maintained perfectly, because any parent child, if you take, parent will be greater, child will be lesser. 42 35, 42 29, 35 10, 35 12, 29 21, 29 15. So any parent child if you take, okay, any parent child if you take, parent will be greater, child will be lesser. So it is perfectly, it is following the property of max binary heap. Okay, so is it everybody is clear up to this? Now we are going to learn how this concept can be forming of this tree. When input is provided, will you be able to form this tree? So I'll just tell you how this can be converted into arrays actually. See, first of all, we'll take the level wise, like order of the tree that whatever we have formed and we will place. For example, we'll take 42, we place it in 0th index. We take 35, we place it in 1th index. We take 29, we place it in 2nd index. We take 10 and we place it in 3rd index. We take 12 and we place it in 4th index. We take 21 and we place it in 5th index. 15 we will take and we will place it in 6th index. So the array that we will be forming will look like this. Okay, the array that we will form will look like this: 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So let the index be 0, 1, 2, 3, 4, 5, then 6. So let me take all the elements like 42, 35, 29, 10, 15. So 42, 35, 29, 10, 12, 21, 15. So this is how we have to take and we have to place it in array. So one thing is, like if I have certain node like 29, if I take, means how will I find which is parent, which is child? That's the one question. So for that we have formula. Suppose if I take any specific ith index value, like 3rd index or 4th index value, if I need to know their parent, okay, which index they will be available, I can use this formula I minus 1 divided by 2. Okay, so this will give you the index of the parent element, where parent element is available. Similarly, this is for parent. Okay, if you want to know the parent. Suppose for the same ith index, if you want to know where the left child is, then you can use this formula 2 multiplied by I plus 1. If you want to know where the right child will be available, you can use 2 multiplied by I plus 2. For example, let me pick an element called as 10. 10 is having 3, right? So 3 means, first of all, parent. So when I is equal to 3, what is parent? I minus 1. 3 minus 1, 2. 2 divided by 2 is equal to 1. So the parent index will be equal to 1. Okay, you can see here in the diagram 10. Okay, parent is 35, which is available in 1th index. Perfectly it is giving. Left child means 2 multiplied by I. So 2 multiplied by 3, 6 plus 1, 7. Then 2 multiplied by 3, 6 plus 2 is equal to 8. So 7 and 8. Okay, so 7 and 8 means there is no index called as 7 and 8 is available, which means that particular node does not have any child at all. For example, let me take 2. I is equal to 2. So when I is equal to 2, what is 2 multiplied by I? 2 multiplied by 2, 4 plus 1, 5. And 2 multiplied by 2, 4 plus 2, 6. So let us go to 5 and 6. 5th and 6th index element, they are the 2 child element for 2nd index value, which is 29. Perfectly it is given. So these are the 3 important formula using which we will be implementing in array very clearly. So if ith index is provided, if you want to find the parent, you go to I minus 1 the whole divided by 2. When I is given, when you want to know the left child index, you go with 2 multiplied by I plus 1. When you want to go with right child, you go with 2 multiplied by I plus 2. Right? So is this clear for you? Is that clear? Okay. When I is 2, who is parent? I minus 1 divided by 2 actually. I minus 1 divided by 2. So I minus 1 is 1 actually. 1 divided by 2 is equal to, it has to be 0 point something, but we'll take only the integer point. So when I is equal to 2, parent is equal to 0th index. So you see here, when I is equal to, the parent is equal to 0. Okay, we will be taking only the floor division. Okay, floor division value we will be picking. See, again I will tell you, after you form like this binary heap in an array, the final array will look like this. So what I'm telling is, if you want to find the parent of a certain element, ith index element, so if you know I value, you take I minus 1 divided by 2, you will find the parent. In that particular index only, the parent element will be available. And if you want to know which index left child will be available, you go with 2 multiplied by I plus 1. Then if you go with the right child, then you go with the 2 multiplied by I plus 2. You will find the index, right child index. Okay, you will find that right child index. Okay, which index the right child will be available. Okay, which index the right child will be available. So these are the three formulas: I minus 1 the whole divided by 2, 2 multiplied by I plus 1, 2 multiplied by I plus 2. Is it everybody clear with these three things? See, these formulas only, like it will be. Yes, this formula will be true for any kind of like tree is converted to array using level order traversal. But like for that, the tree should be level wise, it should be completely filled. Then only like complete array traversal will be very, very, very perfect. Okay, sorry students, there's just got disconnected. Yeah, disconnected again. Okay, fine. So let me go ahead further. So coming here, so I've just taken an array here, same array, same way. Let me use the three formulas: I minus 1 divided by 2, 2 multiplied by I plus 1, and 2 multiplied by I plus 2. And let us check how I'm going to take this array and how I'm going to insert. Okay. So what I'm going to do is, first of all, I'll just take 21. I'll just take a variable I is equal to 0. Okay. So in ith index element, I'll take the first element and I will insert. Very first element, there is nothing to check for. So after inserting the very first element in 0th index, let me increment my I by 1. After incrementing I by 1, I will take the next element 10. I will place it in the present ith index 1. Then after that, I will take child. Okay, C is equal to whatever the present I value is, that I will take to be the same child. I'll consider that to be child. And I'll try to find the parent of that. I know the child index. Now I need to know the parent. How I can know? Child index minus 1 divided by 2. I think there I kept it I. For any I index, if I want to know. Here the index is C. So C minus 1 divided by 2, I will get to know what is parent. So what is C here? 1. So it is going to be 1 minus 1 divided by 2, which is 0 divided by 2. So 0 divided by 2 is equal to 0. So which means parent index is 0. So child is 1, parent is 0. So after you find the child index and parent index, we need to make a checking process. What is the checking process? We need to check whether, let me consider this to be HEAP, heap, name of the array itself. So heap of parent and heap of child, both have to be compared. How they will be compared? Heap of parent and heap of child. If heap of parent is greater, child is lesser, mean no issue. The issue is when heap of parent is lesser than heap of child. When heap of parent is lesser than heap of child, then we can say that there exists a violation. There exists a violation. There exists a violation between the parent and the child. Okay, there exists a violation between the parent and the child. Okay, so if this condition, so we need to check whether this condition is true. If this condition is true, then we need to make a swap between, the parent index and the child index. Okay, so now is it a heap of P? What is parent is 0th index? Is it lesser than C? No. 0th index value is not less than 1th index value. So condition is not true. When condition is not true, you just simply stop and move to next set of I value equal to 2. Whatever is the I value, that will become the child value also, child index also. And what I will take the next element, pick the next element, and I will insert it in the present ith index. After inserting, I know the child index is 2. Child index is 2 means what will be the parent index? Same formula, child minus 1 divided by 2. What is child here? 2. 2 minus 1 divided by 2. What is 2 minus 1? 1. 1 divided by 2 is also equal to 0, only floor division. Okay, 1 divided by 2 is also equal to 0. So child is 2, parent is 0. So take the child value 35, parent value 0th index value is 21. So is it parent index value is 21 is lesser than child index 35? Yes, 21 is lesser than 35. At this point of time, what you need to do? I need to swap between that particular respect to parent and child index. So 35 and 21 will be swapped. So 35 will reach 0th index and 21 will reach, 21 will reach second index. After this, when swapping has taken place, what we need to do is we need to take the present parent index as a new child, because to that place only the child has gone to the parent index only. So that parent index will become the new child. So child will be equal to 0. When child becomes 0, I have to stop, because for child 0 there is no parent is available. There will be no parent. So when child becomes 0, I will stop the entire process and I will just move to the next set of I value, which is 3. So if I is equal to 3, then the child index also will be equal to 3. I equal to 3 means child index also will be equal to 3. Now let me go to third index. Third index, the value is equal to 12. Okay. Third index, the value will be equal to 12. Third index, value is equal to 12. Now after that, what I will do, I have to find the parent index. So 3 minus 1 divided by 2. What is 3 minus 1 is? 3 minus 1 is 2. So 2 divided by 2 is equal to 1. Okay, 2 divided by 2 is equal to 1. So parent index is equal to 1. So when parent index is equal to 1 and child index is 3, what we have to do? We need to check whether this 1th index value 10 is less than the third index value of heap, which is 12. So is it 1 is lesser than third index value? Yes. 1th index value is 10 and third index value is 12. Yes, the condition is true. So we need to make a swap between both of them where this 12 and 10 will be swapped. So 12 will move here and 10 will be coming here. After this, what we need to do, the present process parent will become the next process child. So my child will be equal to 1 because the previous step parent is 1. So child is 1. If child is 1, what will be its own parent? Parent will be equal to child minus 1 divided by 2. What is child 1? 1 minus 1 is 0. 0 divided by 2 is equal to 0. So child 1, parent 0. So compare the child 1 and parent 0. Is it heap of P is lesser than heap of C? Heap of P means heap of 0. Heap of 0, 35. Is it 35 lesser than heap of 112? No, 35 is not less than 12. So condition false. When condition false, I need to stop and I need to go for the next set of I value. So I will change my I to 4. When I becomes 4, child also will be equal to 4. So in fourth index, I will pick the next element, which is 42, and I will place it over here in this fourth index. And after that, if child is equal to 4, what will be parent index? I minus C minus 1 divided by 2, right? So 4 minus 1 is 3. 3 divided by 2 is equal to 1.5. But when you round it off, you will get 1. So for the fourth index value of 42, definitely the parent index is 1th index, which is 12. Okay, so when I just simply 12, is it lesser than heap of C, which is child 42? Yes, 12 is definitely less than 42, so I need to make a swap between both of them. So this will become 12. Okay, so this has become 42. Now after this, present C will become the next process. Present parent will become the next process. Okay, parent is equal to what? 0 divided by 2 equal to 0. So compare 1th index value and 0th index value. When 1th index value is 42, and then when it is compared with this 35, so 42 and 35 has to be compared. When I compare, I see that heap of P, which is parent 35, seems to be lesser than the child 42. So I need to make a swap between both of them. So 42 and 35 will be swapped. So 42 becomes 0th index value and 35 would have come here. And after this process, the present parent will become next step child. So child will become 0. Whenever child becomes 0, I have to stop the process. So child becomes 0, stop the process, and I go to the next set of I value. So next I value is equal to 5. If I is 5, child also will be equal to 5. What is next value? Next value is equal to 29. So I will insert 29 to the present ith index value. After that, I will try child is available in 5th index, means what will be his parent? Child minus 1 divided by 2, which is 5 minus 1 divided by 2. 5 minus 1 is 4. 4 divided by 2 is equal to 2. So the parent node of 5th index value is 2nd index, which is 21. So here what we are checking is heap of P, which is parent index, which is 2nd index 21. Is it lesser than heap of C, which is child index, like 5th index 29? Yes. So parent index, which is 2nd index value 10, is 21 is definitely lesser than 5th index value 29. So what I need to do is I need to make a swap between both of them. I need to make a swap between both of them. So 29 and 21 is swapped. So 21 comes here and 29 goes there. So this present, present child, the parent will become the next process child, right? What is the parent now? 2. So that 2 will become the new child. If 2nd index is a child, what will be parent? Parent will be C minus 1 divided by 2, which is 2 minus 1 divided by 2, which is 1 divided by 2. 1 divided by 2 is equal to 0. So now I will compare 2nd index value and 0th index value. When 2nd index value seems to be, quite lesser. So when you see here, heap of P, parent is 0th index 42. Is it lesser than heap of child, which is 2nd index 29? No, 42 is not definitely greater than 29. Okay, 42 is not definitely greater than 29. Okay, 42 is definitely greater than 29. So you don't want to make any swap here. So let me stop the swapping everything. Then after let me stop the swapping, I'll just go to the next index of I, which is 6. Child is also 6. What is the next element? 15. I'll take that 15 and I will place it here. Now let me try to find the parent index, which is child minus 1 divided by 2, which is 6 minus 1, 5. 5 divided by 2 is equal to 2.5 something. So I'll take it up to 2. So this is not 5 minus 1. This is going to be 6 minus 1. So 6 minus 1, 5 divided by 2 is equal to 2.5, but approximated to 2. Now, after finding a child and parent, I'll compare second index value and sixth index value, which is child and parent. Suppose if heap of P, that is heap of parent, second index value is less than child, which is sixth index. So if second index value is less than that sixth index value, okay, second index value, if it is less than sixth index value, what we need to do? But it is not true here, right? Is it true here? Second index 29, sixth index is 15. Is it 29 is less than 15? No. When the condition is not true, you can just simply stop and you can take your I to next, but I equal to 7 will go out of the boundary. So this is a place where you need to stop. When now you look at the array and also the tree structure, it will be same level wise 42, 35, 29. 42, 35, 29 exactly. Then 10, 12, 21, 15. 10, 12, 21, 15. Exactly the same level wise order of the tree structure only I have got now here. So is it everybody clear with how this array procedure is taking place? Is it everybody clear with this array, like how that binary heap is getting converted to array? Is it everybody clear? If any clarification you have in this array of array implementation of heap, the concept of it, so post your doubts in the chat box. I'll clarify it for you. For every term, the child will be the next parent. Okay. See, see, I'll just proceed with the implementation next. One thing I'll just tell you, like about the parent formula alone, I will just tell you one thing. See, if any ith index is provided, and if you want to find the parent index, you need to do this I minus 1 divided by 2. Whatever you get, that will be your parent index. Similarly, for the same ith index, if you want to know the left child, which index it is available, I need to go with I multiplied by 2, I multiplied by 2 plus 1. It will be one left child index, and R, which is equal to I multiplied by 2 or 2 multiplied by I plus 2, will be the right child. So we'll take one example here. Suppose if I want to know the, like the parent of, like 42, what I will do? The index of 42 is 0. So parent, if I want to find, means I need to do I minus 1 divided by 2. So what is I minus 1? 0 minus 1 is minus 1 divided by 2. Answer will be negative. In that case, we could understand that, okay, this node is not having any parent element. 42 is not having any parent. I can understand. Then I want to know the left child. Okay, 2 multiplied by I plus 1. So what is 2 multiplied by 0? 0 plus 1 equal to 1. So 1 means left child is available in 1th index. Perfect. Same thing, 2 multiplied by I plus 2 means the right child will be available in this particular index. So 2 multiplied by I. So 2 multiplied by I plus 2. So 2 multiplied by I plus 2 means it is going to be 2 multiplied by 0. 0 plus 2 equal to 2. So left child is available in 1th index and right child is available in 2nd index. Perfect for 42. Now let me pick I is itself equal to 1. When I is equal to 1, what will be my parent? I minus 1 divided by 2. So 1 minus 1, 0 divided by 2. 0 divided by 2 will be 0. So 0th index only my parent element will be available for 1. Yes, for 1th index, 0th index is the parent. What about the left child? I multiplied by 2, right? So 1 multiplied by 2 is 2. 2 plus 1 is equal to 3. So 2 multiplied by, again 2 multiplied by I is equal to 2 plus 2, which is equal to 4. So the left child of 1th index value is 3rd index and the right child of 1th index value is 4th index. Okay, in left side index 3rd index I have 10 and in the right side index 4th index I have the value 12. I have the value 12. So this is the formula. When ith index is provided, parent will be available in I minus 1 divided by 2. When ith index is provided, the left child will be available in 2 multiplied by I plus 1. And when ith index is provided, right child will be available in 2 multiplied by I plus 2. That's it. I'll take you everybody to the code editor. We will just start the implementation. Okay, fine. So let me take you people to the code editor. Just give me a minute. So we will implement this in both, like C as well as in Java. We will implement this. Okay. Okay, so now coming here, let me create a new file and let me save this file as binary heap. Okay, dot C I will take it as. Then I'll do the Java implementation also. I'll just do the Java implementation also after this. So now bheap.c hash include stdio.h is a header file, then integer main function. Now coming inside this, first thing I need to know how many elements that we are going to insert in the heap. So integer n I will be declaring and I'll use scanf to receive. So scanf %d comma ampersand n. Okay. percentage d comma ampersand n. So after receiving n, okay, after receiving n from user, now it is time to take a array of that same integer array heap of that size n I will be declaring. And now what I do is I have to insert the element as well, right? So after insertion of every element, what we need to do, that also we need to decide. So first of all, let me run a loop integer I is equal to 0, I less than n, I plus plus. So the first process that what I do is I do the scanf of percentage d comma ampersand arrfi. So I'll receive an element and I will store it in ith index of, not arrfi, heap of I. I'll receive that element and I'll store it in the ith index element of heap in semicolon. After I receive ith index element and I store it in, after I receive element and store it in ith index, then what I need to do is I need to take a variable called as child, and the present ith index will be the child. Okay. Now what I do is for this I need to, I would like to like find the parent. So integer parent is equal to, when I know the child, how will I find the parent index? Child minus 1 divided by 2. Child minus 1 divided by 2. I will get the index of the parent. After you know parent, now you make a comparison whether heap of parent, if it is lesser than heap of child. Suppose if heap of parent is less than heap of child, then I need to make a swap between both of them. So for swapping, let me write a function void return type, and name of the function is swap. And let me take the first parameter integer star a, and the second parameter is integer star b. Then I'll just go with swapping this, whereas I'll take integer temp is equal to star a is equal to star b, then star b is equal to temp. Done. So swapping is done with the help of this thing. Then out of this, I will just inside this function, I'll call this swap function, and I will just simply pass the address of heap of parent index and comma address of heap of child index. That's it. So after I swap between this parent index and child index, okay, after I swap this, I need to continue the process. But if suppose if this condition is not true, means what it means? If the condition, this condition is not true, means it is, it is not, there is no violation is taking place, no swapping is required. We can stop the process and we can go for the next set of I value. So I'll just write this break. And I'm just going to take all these things inside because one, and I will again proceed, right? So I'll just write this while of 1. Okay, I'll say while child, okay, while of child is greater than 0. So child becomes 0, I will stop the process because child 0 means have reached the root node. Once that is okay, when I come to root node, violation is I will stop. That's why we have written break statement over here. Simply change the, okay, child is equal to, okay, child is equal to the new child, again parent will, like if the violation is not taking this true, otherwise this condition becomes false, then we will just come out. Okay, friends, I'll just repeat once, like, because it was just disconnected in between, right? So I'll just again explain this, and then I'll go for the, the test case. See, what we have done here is, first of all, I have received a variable n from user, which is pointing to how many elements we will be receiving for inserting in binary. Then we have taken an array of size n. Then what we do is, for every ith index, first of all, we receive a new element and we insert it in that particular ith index, and we take the same I as the child index. And since until we reach the root node, what we are doing, we are finding the parent for the child index, and we are comparing that parent and child. Suppose parent is lesser, child is greater, means that is a violation in max binary heap. So when this condition is true, I'm making a swap between the parent and child index. If not, I will stop the process. If this condition is not true, what it means? It means that there is no, violation is happening. Max binary heap, properties have been followed properly. In that case, I can stop abruptly. So if this condition is false, means I will just use break statement. I'll stop the entire condition. If not, if this condition is supposed true, I will take this present iteration parent as a new child and I'll continue. And for that new child, again, I will come for the iteration. Again, I'll check whether it is greater than 0. And for that child, again, I will start a parent, find a parent and parent-child comparison. And this will repeat either until if I reach a 0th index, child go to 0th index, or otherwise, if the violation is not taking place. So after this entire process, for every ith index value, if you after you are doing all these things, finally coming out, it is going to form a complete binary tree following maximum binary heap as a property. And so we are printing all the elements of the heap and showing that yes, okay, maximum binary heap has been formed. For swapping, we have used a function over here also. Now let me take you to the terminal, and coming here to the terminal, let me. Okay, I think it is presently in execution mode, right? So I'll take the basic sample test case, which is 21. First of all, 7 elements, 21, then 10, 35, 21, 10, 35, and then it is 12, 42, 12, and then 42. So after 12 and 42, it is 29, 15, 29, and then 15 it is. So have a look at this. We have 42, then 35, then 29, then 10, 12, 21, 15. Same answer, whatever we have got there in the sample test case: 42, 35, 29, 10, 12, 21, 15. 10, 12, 21, 15. Perfect. It's definitely, it's completely working, perfectly. So you look into the main concept over here. The main concept lies inside this for loop only. This complete for loop is the main logic. So look into this complete for loop and tell me if there is anything that needs to be clarified to you in terms of that particular loop. Yes. Next, we will take the same code and we will convert it into Java. But before that, I'll also send this file to you. Receive this file and tell me if there is any, clarification is required. Okay, just let me send the file. Just give me 1 minute. Students, I have shared a file with you, coding file with you. Just tell me in the chat box whether you have received it or not. Just check whether you have received it or not. Then after you have any clarification clear now, then I will go to Java implementation of the same topic. Have you received the file? Confirm it in the chat box. Okay, so now I'll just take the same code and I'll just convert this. Okay, I'll just take the same code and I'll convert it into Java and I'll just show you. I'll just create a new file. Let that new file be bheap.java. So let it be bheap.java. And coming to this bheap.java, first thing is I need to take public class and the class name. Let it be the same file name, which is bheap. And then inside I'll just take a main function. And before this, let me also import. Okay, import java.util.start. Then first thing is for input getting, I need to create an object for scanner class. So let me create an object sc for scanner class. So scanner sc is equal to new scanner of system.in semicolon. So scanner sc is equal to new scanner of system. This is for receiving, like input. We create an object for this, and then after this, let me use sc.nextIntOf. Okay. Using sc.nextIntOf function, I'll be able to receive integer input from user. Let me receive it and let me declare a variable integer n and let me take it here. Apart from that, after receiving, like that, I will just copy all the other remaining stuffs. Okay, I'll just copy all the other remaining stuffs. Let me copy and let me paste it after that. Okay, let me paste all the things after this and I'll tell you what changes have to be done over here. Okay, so now first thing is to declare an array, I should not give the size on left side. I just have to give this empty subscript and I should use the keyword new to allocate memory for it. So new, then I should specify what is the data type and followed by subscript, and here I need to specify what size I need to be allocating memory. Okay, this is how you declare array and you allocate memory for it. Then here again, instead of the scan of what you need to do, we need to use sc.nextIntOf to receive integer. So heap of I will be equal to sc.nextIntOf. This is a function. Then apart from this, I think swap function, we have not defined yet. So better what we will do is here itself we will do this. It is integer temp is equal to heap of parent. Then heap of parent is equal to heap of child. Then heap of child. Okay, heap of child is equal to temp. So swapping has done. So then finally, when coming to printing, we need to use system.out. Okay, so we need to use system.out.print. Okay, system.out.print of heap of I plus then space. So system.out.print of heap of I plus space. So every ith index element I will print and then I will print a space also. Okay, so let us execute this. Okay, so now for here again we will give the same input that we have given over here. We'll check whether same output is coming 7, and the 7 elements I will just take here and here paste it. You can able to see 42, 35, 29, 10, 12, 21, 15. Same output we are getting. So this is in terms of Java. This is the implementation. So have a look at like how we have done the same thing in Java. Same thing. Most probably nothing is changing. So have a look at it. Any clarification with respect to this also, you just tell me. Okay, any clarification, anything additional information that you want to know about this also, please do tell me, please. I'll also send this file also like to you, and people who want Java, you go with it. People want C, you go with that. That's it. So I'll just go with the bheap.java and I'll send you that file also. So I'm just sharing that file. Yes, just check whether you have received that Java file also. Just kindly check whether you have received the Java file also. Please do tell me in the chat box after receiving. Okay. See here, same, same creation of, like heap also. Same creation of binary heap. Okay. Same creation of binary heap. What we need to do is we have another method called as heapify, which will be creating a heap in a better way, faster way, optimized version of this technique, whatever we have done here. So I'll just take you to Blackboard and I'll just show you what is this heapify technique, how we need to do this heapify technique, how it is better than this, how it is going to be faster than this, all these things that, like that we will discuss now. Okay, so let me share you with the Blackboard. So we'll see the concept of that, then the implementation of that, and then we'll just wind up the session of today. I think it will take another 20 to 25 minutes. It will take. So we'll finish it. Okay. Yes. Just 1 minute. Let me share. Okay, I think now, like you see this Blackboard, right? So coming to Blackboard, first of all, there is an operation called as heapify. I'll tell you what is this heapify. Let me take the same value again, 21, then next it is 10, 35, 12, 10, 35, 12, okay, 21, 10, 35, 12, 42, 29, 15, 42, 29, 15, okay, 42, 29, 15. 42, 29, 15. Yes. So 21, 10, 35, 12, 42, 29, 15. Okay. So now coming here, okay, for 21, 10, 35, 12, 42, 29, 15. And this is, like coming. See, coming here, what I will do is in heapify, I will not check while insertion. I will not check anything, whether child is greater, parent is greater, which one is smaller, which one is greater. Nothing I will check. I'll take 21, 10, 35, 12, 42, 29, 15. Means I'll insert it first of all, everything. So 21, then 10, 35, then I'll insert 12, and then insert 42. I'll not check anything. I'll not make any swapping. Then 29, and then 15. I'll insert. After inserting, what I will do is I will just start choosing from the last element. Like I'll choose 15. So after inserting everything, now I'll just choose 15. According to this 15, I will try to check the left and right child. But there is no left child, there is no right child. So I will not do anything for 15. For 29 also no left child, right child, I will not do anything. 42 also no left child, right child. 12 also there is no left child, right child. Now let me come to 35. For 35, both left and right child is there. What we need to do is, whatever I have done, right, there I have taken a child and compared it with parent, bottom to top. But here the comparison is going to be from top to bottom. Like I pick 35, I take the two child, I just find the greater child among that. So the greatest child between 29 and 15 is 29. I take that greater value 29 and I check this 35 with 29. I check which is greater actually. I think 29 is greater or 35 is greater. Sorry. I check whether I just take this greater element among this two child, and the greater element I just take this as child, and this becomes parent, right? So when you take the parent and child compare, which one is greater? Parent is greater, child is smaller. So you don't require any swapping to be done over here. So I'll just not do any process for 35. I'll go to next value, which is 10. Now coming to 10, between the left and right child of 10, which one is greater? 42 is greater. So let me take that 42 as a child and 10 as a parent and compare. So which one is greater? Child is greater, parent is lesser. So when child is greater and parent is lesser, it is not the property of maximum. So we need to make a swap. So 42 and 10 will be swapped. So 10 will go as a right child and 42 will become the parent over here. Now I will not stop. I will take the present child as a new parent, which is 10. I will take it as a new parent, but there is, unfortunately, there is no child is available for it. So I can't do anything. Okay, I'll stop. I'll go to the next element, which is 21. For 21, between the two child we have, which one is the maximum one? 42 is maximum. So let me pick that 42 and compare it with 29. 42 is child, 21 is parent. I think child is greater, parent is lesser. So I need to definitely make a swap. So 42 will become 42 will become a root, and then next here, coming here, like 21 will be coming here. Now after that I will not stop. I'll take 21 as a parent, then I will check which is the greater among the two child. 12 is greater, so I'll take that as a child and I'll make a comparison. Parent is greater, child is smaller, so I think there is no difference over here. So I think no changes will also, like it will occur. No changes also will be occurring. Okay, no changes also will be occurring. So now 42, then left is 21, right is 35, then 21, left is 12, right is 10, then 35, left is 29, right is 15. That's it, done. Now if you look at everything, like it is completely, like 42, if you take both, the child is lesser. 21, if you take both, the child is lesser. 35, if you take both, the child is lesser. So why it is efficient than the previous technique is, for all the 4 nodes, you will not do anything. Am I right? Literally, this is more than half of the element. For more than half of the element, we are not going to do anything because they all don't have left child as well as right child. We'll ignore it. But in the previous case, it is not like that. Whichever element we insert, we will just, like what we will do. We'll go to the parent and we will definitely check. Only for one element, only parent is not available. That is root. But here, more than half of the element, leaf node is not, child is not available. So when you do this, it will be, like literally, it will be 2x efficiency will be obtained. So what is the process? Whatever element is given, level wise you insert, create a tree. Then start picking from the very last element, and whichever element you are picking, try to find the left child and right child. Find the maximum between left and right child. Whichever is maximum, with that you compare the present element. Suppose parent is lesser and child is greater, make a swap. Or otherwise, you just keep continuing. Automatically, you will get. So instead of doing from bottom to top, now we are doing from top to bottom. That's it. Child parent. Again, I convert parent to child. Again, child parent. Then again, I convert parent to child. Again, child parent. Here, parent child. Child will be converted to parent. Again, I will find a child for that. And that child will be converted to parent. I will find a child for that. And it will go from top to bottom. So that was bottom to top approach. And this was, that was bottom to top. And this is going to be top to bottom approach. Right? So is everybody clear with this Heapify technique? Friends, is everybody clear with this Heapify technique? Any clarification with the Heapify technique, post in the chat box. See, and students, is there any, like 1 minute, like there is an issue with attendance. Okay, fine. So what is the issue exactly you're facing? Which date you want to give your attendance? What is the attendance? Just tell me in the chat box. I think one person is asking with, like there is an issue with attendance. Can you just tell me what is the exact issue that you're facing? Have you given your attendance today? Okay, again I will explain. Okay, I'm not able to. Can you just send me your mail ID in the chat box? Just 1 minute. See, students, I'll just do one thing. I'm just posting a Google form in the chat box. What? Just enter your mail ID in that particular Google form, please. It will be easy for me to take and proceed actually. So just everybody fill your mail IDs. Whoever is having login issue, fill your having attendance issue or this login issue you're having, right? So login issue people, you just fill out your mail ID in the link that I have posted in the chat box. Okay, see, friends who see students for whoever I have filled that Google form, right? For them I will be like resolving it, and I'll tell you like so far like nearly 21 people have like responded to that. So like for the remaining people, I'll just explain you this Heapify technique once again. Okay, so let me repeat this Heapify technique once again. So for Heapify technique, what's the first thing that you should keep in mind is, see, for Heapify technique, the one thing that you need to keep in mind for sure is, I take 40. I just will take all the elements as it is, and I will be first of all creating a complete binary tree. No checking I will be doing. Like 21, left of 21 10, right of 21 is 35. Left of 10 is 12, right of 10 is 42. Left of 35 is 29, right of 35 is 15. Like that I'll insert. After inserting, what I will do is I'll start choosing element from the last place. And for whichever element that I'm choosing, I'll check whether left child, right child is available or not. If it is left child, right child is available, I'll find the maximum of the left and right child. Suppose if I take 35, some element is available here, I'll try both the left child, right child, I'll take which is the maximum of it. And which one is the maximum, with that I will compare the present element, and I'll check whether the parent and the child, I'll consider the downside as a child and the upper one as a parent, and I'll check whether the parent is greater than child. Suppose if parent is greater than or equal to child, then it is okay, it is following the property of maximum binary. But if not, but if parent is lesser and child is greater, then there is some issue. So we need to make a swap between both of them. Then we need to make a swap between both of them. So 35, 29, there is going to be a swap. So 29 will become a parent and 35 will become a child. This has to happen for every set of elements. So there in the okay, so there in the usual old process, what we did is, whenever inserting, we were taking the element and we were comparing it with parent index element, and if there is any violation was taking place, we were just swapping. There is only one node, that is the root node is the only node which does not have any parent. But apart from that, every node is also having parent. But when you take this technique, here we are taking a parent and we are comparing it with child. So child is very important here. So if you see, there is nearly 4 element which is not having any child, which is more than half. Total 7 element. In that 7 element, 4 element is not having left and right child. So we don't want to do any process for those 4 child. Only for the remaining 3 element only we need to do the entire process. So literally we can avoid half of the element. We can avoid the process for half of the element. That's why I say this technique is going to be efficient over the last technique. So the process is, you pick every element, and the element you have to compare it with your both left and right child. So whichever one is maximum, you just find the maximum of the left and right child. Which one is maximum? Compare it with the present element. If the present element you consider to be parent and the left or right element, which one is maximum, you consider to be child. Parent is greater and child is lesser, means absolutely fine. But parent is lesser, like a child is greater, means then you need to make a swap between both of them. So this is the process. This is the technique. of Heapify is all about. Okay, so this Heapify technique tomorrow we will just continue Heapify and its respective implementation. We will just continue it in the next session. Okay, so we'll just maximum, like we'll just wind up the session over here.